Hello everybody, welcome back. Today we're going to be taking a look at a line integral problem and how different paths create different results. Okay, so for this problem here, we are supposed to find the work done by this force here um, in moving an object from 1, 0 to 0, 1 along each of these three paths. And part A is a straight line from between those 2 points. B is a circular arc, and C is just moving along these lines themselves. Okay, so to start off with, we need to find our f dot dr, and remember that our r is, I guess we could give it a little vector hat there. We should give those two. Our r is simply the vector from the origin to our point. So if we dot these two vectors, what we get is, so we multiply these two together. Oh yeah, dr. Remember, it's dr, not r. So dr is dx plus dy. And then we multiply the components with each other and add them together. So we get this here, dx, and we don't keep the I in anymore. And then x squared dy, and we don't keep the j hat in there either. Okay, so starting out with part A. This has two different variables, but thankfully our line here gives us an equation that relates our x and y, so we can actually solve this problem. So for this problem, our y equals 1 minus x, and we're actually starting off here at x equals 1 and then going to x equals 0 from x equals 1 to 0. Okay, so if this is true, then our dy is equal to negative dx. And we need to find that because not only do we have x's and y's in this equation, we also have dx's and dy's. Okay, so rewriting this, actually, yeah, so we'll just write it in integral form right away. So adding up our f dot dr is going to give us our work. And this is the same as saying, remember, from 1 to 0, not from 0 to 1. From 1 to 0 of, and we're going to substitute in for, so everything's in terms of x. So 2x, 1 minus x, minus 3. We'll take care of the dx in a little bit. Plus x squared, and this is a negative dx actually, so negative x squared, and then this whole thing is multiplied by dx, but the integral kind of takes care of that part of that for us. Okay, so rewriting this, we get 1 to 0 of 2x minus 2x squared minus 3 minus x squared dx. And this is the same as, well, actually, yeah, so we can just add these two together. So we'll take the integral of each of these parts now. So this is going to be x squared, and the integral of the negative 3x squared is going to be negative x cubed, and this is going to be minus 3x. This is all from 1 to 0. Finally, we can plug in, remember that this is a positive 0 and this is minus what it is at 1. What we get is a 1, no, we get minus 1 plus 1 plus 3 equals 3. So that's our answer for part A. For part B, since this is a circular arc, this one is better served by plugging in or transforming it into polar coordinates. So we're going to do just that. So our r for this is 1, the radius is 1, and that's constant because it's a circular curve. So we'll do this transformation like cosine theta y equals sine theta, and we're going to have to get dx and dy also. Dx equals negative sine theta d theta, and dy equals cosine theta d theta. And remember to keep the d thetas around too, because it is technically required by the chain rule. So if we're doing it like this angle is a 90-degree angle, so that's pi over 2. So we're going from, so r is constant, but theta is varying from 0 to pi over 2. So it's going to be our constants of integration. No, not our constants of integration, our integration limits. And so we're going to have to substitute into this equation everything that we have here. So this is going to be 2 cosine theta sine theta minus 3, and then times our dx, which is minus, well, it's times negative sine theta d theta. And then the second part of it is cosine squared theta times, well, cosine theta d theta. Okay, so this one really tests you on how well you remember all your different techniques of integration. So what we end up with here after we simplify it is integral from 0. Well, yeah, so I'm going to be splitting up the integral into a few different pieces. So this negative 3 gets multiplied by the negative sine theta, so we have 3. Actually, I could put that in front, but it doesn't matter. 3 sine theta d theta. And then this section here is going to be 2, or well, yeah, negative 2, which I can pull out front, negative 2 cosine theta sine squared theta. And this one isn't too bad either. What I'm going to do is I'm going to u substitute, which is a very good first try if you don't know how to do an integral. So our u is going to be sine theta, and our du is going to be cosine theta d theta. So actually, yeah, so these limits of integration, since I'm u substituting, are not going to be the same as they were. But we can plug them, the previous ones, into this equation to get our new ones out, which I will do. Sine of 0 is 0, and sine of pi over 2 is 1. So these are correct limits of integration now that we've transformed them. And so we have a u squared, because we are saying that u is equal to sine theta. And then the cosine d theta gets eaten up into the du right there, because it was multiplied by a cosine, but we substituted in for u, so we're substituting, yeah, so it's no longer a factor. And then this cosine, the cosine cubed portion, yeah, well, it's certainly fun. So, cosine cubed theta, okay. So now we can do these first two and the last one. So what we get here is 3, actually no, it's negative 3 cosine theta, and this is from 0 to pi over 2. The second one is 2 times, or yeah, negative 2 times u cubed over 3 from 0 to 1. And then this last one is 3/4 sine theta plus 1/12 sine 3 theta from there to there. Yeah, I'm not going to go through how to get that at this stage. So this is equal to so cosine of pi over 2 is 0, but cosine of 0 is 1. So because you're subtracting that, since it's at the bottom of the limits of integration, you end up with a positive 3. And then this middle one at 1, this is negative 2/3, and then at the bottom it's nothing, so 2/3 there. And then this one, we'll take this piece first. These limits apply to both of these pieces. So sine is 1 at pi over 2 and 0 at 0. So this is plus 3/4, and then this last one, so it is negative 1 at 3 pi over 2. So this ends up being a negative 1/12. And when you add these all together, you end up, so these add together to be a 3/4, and so it cancels out with this one, so you end up with 3. So these paths end up using an equivalent amount of work. Well, I mean, not actual, you know, they take a lot more effort. It takes a lot more effort to do B, but it takes the same amount of work to push it there on each path. And then for C, which is maybe looks a bit more complicated, but is actually not as bad. All we have to do is split the two integrals at that point there. So going from here to here, x is equal to 1 and dx is equal to 0. So doing the integration, we're doing this in terms of y. So this is from 0y to 1y. And so this term becomes, well, no, actually, well, yeah, this whole term becomes 0 because this dx is 0, so this is the only term that matters. So we end up with 1 dy. And this is 1. And then for the other section here, from here to the end, y is equal to 1 and dy is equal to 0. Okay, and then for this one, we're integrating with a dx. So we're actually going from 1 to 0 as far as x is concerned. So 1 to 0. And that's important. So substituting in here again, this term doesn't matter because dy is 0, but this term does matter, so you get 2x times 1 minus 3 dx. Yes. So integrating this is not that difficult, provided that you already know how to integrate in the first place. So you end up with x squared minus 3x from 1 to 0. And this gives you, so at 0, this is all 0. And then at 1, this gives you, remember since you're subtracting the bottom one, it gives you a negative 1 plus 3. Yeah, so obviously this gives you 2. So now that we have these answers here, what we do is we take each of these here and we add them together to get our total work done. So obviously 1 plus 2 equals 3. So actually, in this case, all 3 of these different paths gave us the same amount of work to get from the beginning point to the ending point. This is not always the case for vector fields, or I guess you could call them a force field in this case. It all depends on properties of the vector field, something that we call whether it's conservative or not. So, because you can imagine that if you took a longer path on a on a force that, or on a force field that had a frictional force, you'd have to use a lot more effort than if you took a direct path. So, yeah, in this case, this turned out to be the same actually for all 3 paths. So, thank you everybody so much for watching, and I'll see you again next time.